Hi guys, Sean Alexander here with Alexander Tutoring, and today's date of the Relativity lectures, and today's going to be super cool. So last time we talked about the light clock. Today we're actually going to derive, we're going to use some math today to show how much time the light clock takes to tick. But first I just want to go over one point one more time because it's really important. And again, the two postulates proposed by Einstein, the special theory of relativity, are one, the speed of light is constant for all observers. So basically, no matter how you're moving, if you measure a light beam, it's going to come out to the speed of light no matter what. And two is the laws of physics are the same in all non-accelerating reference frames. And what that means is if you're going at a constant speed, like for example in an airplane, there's basically no way to figure out that you're moving if you don't look outside and you assume that there's no vibration. In other words, any experiment you do on the airplane should occur basically exactly the same as it would on Earth, assuming no vibration. Okay, and that creates a huge paradox. And I'm going to show this to you one different way just so you really get it. Now, here's my train, right? And there's a guy in the train. And this time I'm going to say the velocity of the train is just under the speed of light. So the train's going almost the speed of light. So I wrote here C is the speed of light minus 1 meter per second. So let's just say the train's going 1 meter per second underneath the speed of light. Okay, and the guy in the train is going to throw a ball. And let's say he can normally throw the ball at 10 meters per second. Like if he was here on Earth, he could throw the ball at 10 meters a second. So the guy in the train is going to throw the ball, right? And question one is, what does the guy in the embankment see? So he throws the ball, let's just say at 10 meters per second. What does this guy see? Well, you'd think he'd see the speed of the train, which is c minus 1 meter per second, plus the speed of the ball, which equals the speed of light plus 9 meters per second. Okay, but according to rule 1, not possible, right? You cannot violate the speed of light. That would be going faster than the speed of light, which is another part of law 1 there. Okay, and we all agree that you cannot go faster than the speed of light, so it seems that law 2 is violated. Okay, well, maybe the ball, from the outside observer, maybe the ball just doesn't go 10 meters a second. Maybe it goes 0.8 meters a second. But wait, now we have to jump into the frame of the guy in the train. The guy in the train, as far as he's concerned, it's just like standing still. He has no way of knowing that he's moving. It's exactly so. What that means is everything should go down exactly like it would if he went it on the ground. So my question is, he throws the ball like he normally would on the ground. What magic force of nature is going to prevent it from going the normal 10 meters a second like it would if he threw it on the ground? He doesn't know he's moving. He should be able to throw the ball at 10 meters a second, no problemo. But the problem is when we go to the frame of the guy watching, it violates the speed of light. And so that shows a paradox, okay? And that's the paradox we're going to try and resolve. And again, we introduced last time this way of measuring time. Remember, I really led you guys up. What is a second? How do you measure a second? And, we came up with this idea of simultaneity, meaning we compare one motion with another. We show up to class at 8 a.m. at a certain location. When the spinning thing on the wall lines up, the hands line up at 8. Okay, so we invented a clock last time that works like this. There's a light bulb, a mirror, and a detector. And basically the light bulb flashes at 1 second intervals, right? And the light goes up, down, and then the detector goes click. So as the light flashes every second, we go click, click, click. That's a clock, just like any other clock, right? It's ticking off seconds. So that's one way to measure time. Okay, and so the guy in the train, if we put this clock in the train, he's going to see the light go up, down, click, right? And we're going to just say this train has height h, okay? Now the interesting thing is what does the guy on the ground see? Well, the train's moving, right? With speed v. And so here the light flashes, but now the train's moving as the light makes the journey, right? So what he's going to see over the course of the tick is this. He's going to see the light travel in a triangular path, right? He's going to see go up to the top, bounce off the mirror, and come back down to the detector, and the detector goes click. Now, if rule 1 is true, the speed of light is the same for all observers, we notice that, well, the outside observer sees the light travel a longer distance because this distance here is longer than the up-down distance here. Okay, but if both the guy inside and outside the train have to agree on the speed of light, should it not take longer for the light to travel the longer distance to the guy outside, thus increasing the amount of time between clicks? So in other words, their clocks aren't going to agree. The number of ticks on one clock to the guy inside is ticking at one rate, and to the guy sees it outside, it's ticking another rate at another rate if we agree that the speed of light's the same. So what we're going to do now is actually calculate the exact difference in the amount of time of the clicks, okay? And we're only going to use high school math. Now, granted, you got to be good at algebra, and you got to know the Pythagorean Theorem, but we are using nothing outside of high school math right now, okay, guys? And we're going to get an insane result. So first, let's do it the easy way, which is in the train. What does the guy in the train calculate? The other equation we're going to use? Okay, so here's the equations we're going to use. We're going to use algebra. We're going to use the Pythagorean Theorem, which I'm going to assume you know for now. I'll do a video on this later. And then we're also going to use just basic speed equals distance over time. That's the basic non-accelerating speed equation. You use it on the freeway, 55 miles per hour, miles a distance per divided by an hour of time. Okay, again, we said that the height of the train from the floor to ceiling is h. And we're going to say the light roughly just goes straight up and straight down. We're going to say that's a straight line up and down. Okay, so I'm going to solve for t here. So I'm going to multiply both sides by t to isolate the t. So we get t times s equals d. And then I'm going to divide both sides by s to isolate the t. So the time is distance over the speed. So how long does it take to do a click? Well, what's the distance that the light travels? The time to do a click, well, it goes up a distance h and down a distance h, right? So the distance that the light beam travels from the light bulb flashing to the click is twice the height of the car. What's the speed of the light beam? By definition, the speed of light. Okay, so we say that the time between clicks for the observer in the train is twice the height, because the light goes up, down, over the speed of the light, which is c. Okay, now we're going to do the same exercise for the guy observing outside the train, which is a little more complicated. So what does he see? He sees the light follow this triangular path, right? Because so here's the mirror, here's the light bulb. Oops. Away. And here's the detector, right? Because just think of like throwing a ball straight up and straight down while the train's moving, you're going to see it trace out this triangular path, right? So this is what the guy from observing from the embankment sees. And again, he's just following the beam of light with his eyeball. So as the light travels, it goes up to the top of the train, back to the detector. Again, this is still height h. Okay, so we're going to try and now calculate, assuming the speed of light's the same for this guy, the time between ticks. Okay, so what we notice here is we have a triangle, right? So the train was here when the light left the light bulb, and the train's here when it gets all the way to the detector. Because why? Because the train's moving at speed, we're just going to say v, okay? So what's the length of the base of the triangle in terms of v? Okay, so we're assuming the train is going at constant speed. So we're going to use our speed equals distance over time formula. Okay, and then if we multiply both sides by t, we find that distance, that's what I'm trying to find, equals speed times time. Right, I want this distance, the base of the triangle. Okay, well that should be the speed of the train. So d equals the speed of the train, which we're calling v, right, times t, except, and that's t would be the time between clicks, but this time I'm going to call it t prime to differentiate it from the first t that we found, because they're not necessarily the same. We're arguing that for the case of the observer outside the train, he's seeing this light beam travel farther, and so maybe it takes longer to make it to the detector. So I'm going to make it t prime to distinguish it from the first t. Okay, so the base of this triangle has length, the velocity of the train, times however long it takes for the thing to do one click for the guy outside the train. That's the base of our triangle. The height here, well, that would just be the height of the train, right? And maybe I should draw this a little better just so it makes more sense. So if we're looking at it this way, it's more like this, right? Here's the train when sorry guys. Okay, so on the left is the train right when the light bulb flashes. On the right is when the light beam makes it all the way to the detector. Okay, all right, so we have two triangles here, right? We'll notice we have two right triangles. Okay, let's just look at the first triangle. We know the height on the right is h. What's the length of the base of the triangle on the left? Well, it's just half of the total distance, right? So we know the total distance is vt prime. So this must be vt prime over 2, right? Half that distance. Now we're going to find the length of the hypotenuse of the triangle, for which we'll use the Pythagorean theorem. It's a right triangle. That's where we use Pythagorean theorem. A squared plus b squared equals c squared, where a and b are the legs of the right triangle and c is the hypotenuse. Okay, so we found the legs. We can call a is this guy, right? Vt prime over 2 squared plus b squared, right? That's the other leg of the triangle, so we'll call it hb, h squared, equals c, not to be confused with the speed of light. That c is just the length of the hypotenuse, right? So I'll call that d1 for now. Okay? Squared. Okay? So d1, the length of the hypotenuse, equals the square root. We're going to square root both sides. Okay, that's d1. And what we really want, we'll call this d2. D2. That's the other hypotenuse. Because really what we want is the total distance the light beam travels, right? It goes here and then here. Maybe we'll switch some color there. The light beam goes here and then here. And we want the total distance it travels, which is simply twice d1, right? It's just double what we just found, right? So d total, I'll just call it dt for the total distance, which is d1 plus d2, is simply twice what we just found. Okay. Finally, let's see. We're going back to our formula here. What we want to find is t prime. Okay, so looking at this formula, t prime, just rearranging it, is d, that's d total, that's the total distance over the speed of the train. Excuse me, not the speed of the train, my bad. We want the time that it takes the light beam to travel the whole distance, right? So the distance it travels is d total. The speed of the light beam is c. So t prime is d total over c, where d total we just found, right? That the total distance that the light beam has to travel is 2 times okay, and then the whole thing divided by c. So I'm going to put it divided by c here. Okay, so we're going to compare that. Again, that's the time that the outside observer sees between clicks of our light clock. What we're going to do is compare that to the result we got for the inside observer, this guy. He got a time of 2h over c. Okay, and what we want to do, again, is compare the two times. The guy inside the train only sees the light beam go up and then down, and he measures it moving at the speed of light, so he sees it take a time 2h over c. The guy outside observing the light clock sees the light travel this different path, like this, right? And so he sees it take a different time, assuming that he also measures it, the beam to be moving at the same speed of light, t prime. The last thing I'm going to do is eliminate h. H is the height of the train, right? Because we want to compare t and t prime basically to see how they differ. Okay, so h is kind of random. That's just a random height of the train. So what I'm going to do is solve for h here. So I'm just going to multiply both sides by c over 2. To get these cancel. And the height is ct over 2. We're now going to substitute this value, if you remember your substitution from algebra. Again, this is all high school math. And for h right here. Okay? So we get t prime equals 2 over c root vt prime over 2. I think I'm missing a squared. This should have been squared. My bad, guys. Sorry about that. Squared. Plus, here I'm substituting this in for h. Okay, so for h, we're putting in ct over 2 squared. Okay, and now it's just down to algebra, guys. We're just going to simplify some stuff. So again, you have to be good at algebra, but again, this is all high school level technically. 2 over c. Now I'm going to square the first fraction. We square the top and square the bottom to get v squared t prime squared over 4. And I'm going to do the same thing with the other guy. We're going to square the top and the bottom to get c squared t squared over 4. We have here a common denominator, which is nice. Okay, yeah. So the fractions are both over 4. We have a common denominator. Okay. Now you'll notice, well, here, we can go ahead and square root the top and the bottom of that fraction. So when you have the square root of a fraction, you can put the square root on the top and the bottom. But the square root of 4 is just 2. So we have this. Now you'll notice we have a t prime here, but we also have a t prime locked inside of our square root right here. That's a t prime right there. And we want to solve, sorry, and this is t squared. Excuse me. So remember, there's two t's. There's t prime, the time that the clock takes to click from the guy observing outside the train, and there's t, the time it takes the clock to tick from the guy inside the train. So what we want to do is find the relation between t and t prime. So we really want to do is solve for t prime, but I have a t prime solved for out here, but there's another t prime locked in the square root. So we got to get those two t primes together. So the first thing we need to do is undo that square root to get to that t prime. So I'm going to go ahead and square both sides of the equation. So we get 4 over c squared, and then the square root just gets rid of the square root on top. 4's cancel. That's nice. Good. So now look what we have. V squared t prime squared over c squared. I'm just distributing the 1 over c squared in front. And look how convenient that is. Boom. We're getting there. Okay, now we have t prime on both sides of the equation. Whenever you have a variable on both sides of the equation, you want to get them all to the same side. Okay, so I want all the t primes on the same side. So I'm going to subtract that term from both sides. So on the left-hand side, we get t prime minus v squared equals t squared. Okay. On the left-hand side, there's a t prime common to both terms, so we can factor it out, the t prime. That's why we wanted to get everything on the same side. To get 1 minus v squared over c squared equals t squared. Finally, we can divide by the thing in parentheses. Again, we're trying to isolate the t prime. Divide both sides. What you do to one side, you do to the other. Works all the way up until higher level stuff. Cancel. Finally, we have isolated t prime squared equals 1 over times t squared. We're right there. Last step. Square root both sides to get rid of the square. Woo, we made it, guys. Check this out. Look what we get. T prime equals. Technically, you have to do a plus or minus when you square root both sides, but we're going to assume we can disregard the negative case. So we can square root both of these guys. We get t, square root of t squared is t, over the square root of 1 minus v squared over c squared. Boom, done. And what we have just derived, folks, from first principle is Einstein's time dilation formula. And what this, the insane, miraculous, ridiculous result that this states is, again, one more time, what's t and t prime? T is the amount of time it takes for the light clock to do a click as measured by the observer inside the train. T prime is the amount of time for the clock to do a tick as measured from the guy watching from the embankment. And you'll notice they're not the same. They're not the same. Their clocks are not measuring time in the same way, meaning if the guy did his trip on the train, the guy inside that train, he did his trip, counted the number of clicks on his clock, and this guy outside the train counted the number of clicks on the clock, and they went back and compared notes later, the number would disagree. They cannot agree on, they do not agree on the time that went by. So what's the resolution to how can the guy in the train throw his ball at 10 meters a second like he does on the Earth, but the guy outside watches him do it without violating the speed of light? The answer is that they do not agree on the time coordinates. So they're not happening at the same quote-unquote time. Okay, so that's one of the big crazy discoveries of relativity. Anyway, just real quick, just so we can see, looking at the term here, v is the speed of the train, right? So basically t prime is going to be larger than t, because if let's look at a really quick case and then we'll finish up because this is a long one. What if v was let's say 0.5 the speed of light? That's the speed of the train. The train's moving half the speed of light. Well, then t prime equals t over 1 minus, so v is 0.5 c squared. Okay. Uh, 0.5 squared is just 0.25, half of a half. Okay, you can see the c squared's canceled. Square root of 1 minus 0.25. This is what we get if we're going half the speed of light again. 1 minus 0.25 is 0.75. In case you don't know what the square root of 0.75 is, either do I. So I'm just going to use my calculator real quick. Hang on 1 second. Sorry guys, I should have had this ready. Point. Roughly 0.87, rounding here. And 1 divided by 0.87 is roughly, I'm rounding here. Okay, so if you're going half the speed of light, if, for example, if 1 second, if t was 1 as measured by the guy inside the train, t prime would be 1.15. In other words, if you're going half the speed of light, what is 1 second, what is 1 second to the observer in the train is 1.15 seconds to the observer outside the train. They do not agree on time. Okay, that was a long one, guys. If you stuck with it, thank you so much. We'll talk more about the consequences of the time dilation formula, which we just derived, next time. Again, I know there's a lot of math in there, but it's all high school math. And that's one of the cool things about it is you can get this crazy Einstein result that changed the world from just high school math. All right, guys, thanks for sticking with it. I'll keep it shorter next time. Take care. Bye.